Welcome to the deep dive, where we cut through the noise, bypass the jargon, and really try to get right to the core of what truly matters in complex topics. Today, we're taking a truly deep dive into a fascinating, yet maybe often overlooked, corner of artificial intelligence.
Okay.
How we actually know if our AI models are doing their job well.
Right.
It's not just about building a smart system, right? It's about rigorously testing and continually verifying that it's actually smart and trustworthy.
That's absolutely right. We're talking about model evaluation and machine learning, which is, the absolutely crucial process that determines whether an AI is truly reliable, accurate, and importantly, aligned with its purpose.
Okay.
Imagine you're a world-class chef,
Well,
right? And the ML model you've built is your brand new signature recipe.
love the analogy already.
Yeah, so model evaluation isn't just a casual taste test. It's the entire rigorous quality control process for that recipe. It's the difference between a dish that sounds good on paper and one that consistently delights your customers and delivers on its promise every single time.
That chef analogy immediately makes it click. It makes total sense.
Good.
So for this deep dive, we've pulled together insights from, well, a variety of sources on MLOps and model evaluation to really unpack the what, why, when, how, and who of this vital step.
Yeah, the whole picture.
We'll explore why it's far more than just a technical detail. It's really a foundational pillar of trustworthy AI.
Absolutely.
We'll uncover some of the trickiest challenges involved, and then we'll look at how advanced platforms are making this complex process more effective and, well, efficient.
And by the end of this deep dive, you, our listener, should have a crystal clear understanding of how these powerful AI students are graded,
Right, how they get their report card.
Exactly. What critical pitfalls to watch out for, and why this entire process is essential for anyone building, deploying, or even just interacting with AI in the real world. It's about moving beyond simply having an AI model to genuinely trusting that model to deliver real value.
All right, let's unpack this. Let's get right to the essence, the core of model evaluation, ensuring AI quality and reliability. So let's start with the absolute foundation. We hear a lot about AI and machine learning, obviously. But what exactly is model evaluation? How do we, quantify if these complex systems are actually performing?
Right. So at its most fundamental, model evaluation is the systematic process of figuring out precisely how well a machine learning model is performing its intended function.
Okay.
It's not a subjective feeling like, I think it's good.
Yeah.
It's a detailed objective assessment.
Data-driven.
Exactly. We're asking some really critical questions here. First and foremost, is it accurate? Does the model consistently make the correct predictions most of the time?
Right.
Think back to our chef. This is like asking, does your signature dish consistently taste good? Does it hit the intended flavor notes for, say, the vast majority of your diners? A prediction model for stock prices, for example, might be evaluated on whether its predictions closely match the actual future prices. Is he getting it right?
So it's about a consistent pattern of correctness, not just like a lucky guess here and there.
Precisely. Not just luck. But what about consistency, even when things aren't perfect?
Yeah.
Or when the data isn't perfectly clean?
Yeah, that's a good point. What about reliability then?
That's where reliability comes in. Is it reliable? Does the model perform consistently, even when faced with new, slightly different, or maybe slightly messy data?
Okay.
To use the chef's analogy again, does your cake recipe work perfectly every time, even if you switch flour brands, or maybe if the temperature in the kitchen fluctuates a bit that day?
Right, things aren't always ideal conditions.
Exactly. An AI model needs to be robust enough to handle the natural variations found in real-world data, not just the perfectly pristine, idealized data it was initially trained on. If a model only works under ideal, sort of laboratory-like conditions, its real-world utility is severely limited.
It's basically useless then for practical stuff.
Pretty much, yes. For many practical applications, it would be.
And beyond the purely technical aspects, accuracy and reliability, you also mentioned something really important, aligning with business goals. Why is that considered part of evaluating an AI model? It seems almost separate.
But it's where the rubber meets the road,
Yeah.
right? Where the so what truly matters.
Okay.
Does it align with business goals? Is the model actually helping achieve its intended real-world purpose?
Like making money or saving time.
Exactly. This could be increasing sales, improving customer satisfaction, optimizing supply chains, streamlining operations, you name it. For our chef, does that exquisite cake recipe fulfill its ultimate purpose Perhaps being a highly profitable dessert for your bakery that keeps customers coming back.
All right, does it sell?
Does it sell? Or maybe it's a unique selling proposition for a new cafe. An AI model might be incredibly accurate in a purely technical, statistical sense, maybe 99% accurate.
Mm-hmm.
But if its predictions don't translate into tangible business value, say reducing operational costs by a significant margin, or improving efficiency, or genuinely enhancing user experience,
Then what's the point?
exactly, then it's not truly successful from a strategic standpoint. This ensures the technical performance is directly tied to the strategic objectives. It connects the tech to the value.
It's fascinating how it bridges that gap from complex algorithms to like real-world measurable impact.
It had to.
So why is this entire process model evaluation absolutely pivotal? You might think, okay, I built the model, I'm done, but clearly that's not the case.
Oh, not at all. Not even close. It's absolutely foundational for several key reasons, and honestly, underestimating its importance can lead to significant problems down the line.
Okay, like what?
Well, first, it provides a clear performance check. It gives you that tangible scorecard measuring specific metrics that tell you exactly how well a model is performing against its objectives.
Right.
Without this, you're essentially flying blind. You simply don't know if your AI is hitting its targets or maybe missing them wildly.
Which could lead to bad decisions or wasted money.
Absolutely. Misguided business decisions, wasted resources, you name it.
So it's like the dashboard in your car. It tells you if your high-performance engine is running optimally, not just that the car starts.
Precisely. Great analogy. Second, it's absolutely crucial for ensuring generalization.
Generalization. Okay, what's that again?
This means confirming that models work on new, unseen data, not just the data they practiced on during training.
Ah, right. The real-world data.
Exactly. This validates its real-world applicability. Think of that student who aces every single practice test,
Uh-huh.
but then completely fails the actual exam because they only memorize the specific answers from the practice test.
Okay, I know that student.
We all do. Good evaluation ensures the model can actually pass the exam in the unpredictable, often messy real world.
Right.
If a model only performs well on the data it has already seen, it's essentially just memorizing, not truly learning.
And it'll fail spectacularly when it sees something new.
It will. It's a recipe for disaster in dynamic environments,
Hmm.
which means it's fundamentally useless in a real, constantly changing environment.
Got it. What else?
Third, it's indispensable for model selection. When you're tackling a complex problem, it's pretty rare to have just one single model candidate.
You usually try a few different approaches.
Exactly. Data scientists often develop multiple models, maybe with slightly different architectures or training approaches, all aimed at solving the same problem.
Okay.
Evaluation provides a fair, objective way to compare these candidates directly and select the best performer for deployment.
Makes sense.
This saves significant resources and, importantly, prevents rolling out a suboptimal solution that might not work as well.
Like having 5 different cake recipes for your bakery.
Yes.
And rigorously taste testing all of them to confidently pick the one that consistently gets the highest ratings and happy customers.
Perfect. You're picking the winner based on evidence.
And it sounds like this isn't just a one-and-done kind of assessment, right? It seems like it contributes to ongoing improvement.
That's a critical point. Fourth, for continuous improvement. Evaluation isn't just for the initial launch. It enables you to catch problems after a model is live in production.
Like when it's out in the wild.
Exactly. Things like performance drops due to shifting data patterns. This is often called concept drift or data drift. They're actually quite common.
Mm-hmm.
When evaluation signals a decline in performance, it immediately tells you, hey, maybe retraining or recalibration is needed.
Okay.
It's like a popular restaurant dish that suddenly starts getting less enthusiastic reviews.
Right.
The chef doesn't just ignore it.
Right.
They get customer feedback, they investigate if ingredients have changed or maybe customer tastes have evolved, and then they refine the dish.
Adapting to reality.
The world changes, the data changes, and your models must adapt to remain effective. You can't just set it and forget it.
So it really functions as this perpetual feedback loop, not just a static check at the beginning.
Precisely.
And this must be absolutely vital for building confidence, right? Especially among business leaders and the people making the big decisions.
It absolutely is. Fifth, for informed decision-making, robust, transparent evaluation results build immense confidence. Business leaders can make far more informed decisions about how to use a model when maybe it needs an update, or even if they need to adjust their broader business strategy based on its real-world performance metrics.
Right.
Imagine trying to make a multi-million-dollar business investment based on a recipe you've never actually tasted, or one that has a really inconsistent track record.
Yeah, no thanks.
Evaluation provides the objective data and the assurance needed to trust the AI system and integrate it meaningfully into core operations. It gives you that proof.
So putting it all together, what does this mean for the overall impact of AI in, say, an organization?
Well, the overall impact is profound and really far-reaching. Model evaluation ensures that AI models are not just technically sound, but are truly effective, adaptable, and achieving their intended purpose.
Okay.
And that benefits all involved stakeholders, from the data scientists who build them, to the business users, to the end users who interact with them daily. It prevents wasted development resources, it significantly mitigates risks associated with poor performance, and ultimately ensures that AI systems are not merely theoretical constructs, but powerful, reliable tools delivering measurable, sustained value in the real world. 2. The when and how of evaluation, the life cycle and techniques.
So we've thoroughly explored what model evaluation is and why it's so critical. That's super clear now. But let's talk about the when. Is this something you do just once, check a box, and then forget about it? Or is it more continuous?
It's definitely, unequivocally, a continuous process, not a singular event. Think of it less like a final exam at the end of a course, and more like a student's entire educational journey. You wouldn't just grade them once at the end of high school and assume they're set for life, right?
No, definitely not. There are quizzes, midterms, ongoing feedback.
Exactly. There are various critical checkpoints along the way.
Okay. So what's the first major checkpoint?
The first key stage occurs after initial training, but crucially before launch.
Yeah.
This is your rigorous pre-flight check.
Right.
It's your internal taste test before you ever serve that cake to actual customers.
Okay.
Once a model has been trained on its data set, it's extensively evaluated to determine if it's, ready for prime time. Its performance metrics, accuracy, precision, recall, all those things we'll discuss are meticulously compared against other potential models developed for the same task.
So you pick the best one.
Yeah. This comparison helps in selecting the best performing model to deploy, ensuring you're putting your strongest foot forward. This is where you catch fundamental flaws or limitations before they ever impact real users or critical business operations.
Makes sense. You wouldn't open your bakery with a recipe you haven't thoroughly vetted internally, would you?
Exactly right. You'd taste it yourself first multiple times.
And then once it's actually out there, interacting with the real world, what happens then?
That brings us to the second and equally crucial stage after deployment, through continuous monitoring. Once a model is live and making predictions in a real-world setting, its performance must be continuously evaluated using new, incoming real-world data.
Right. The data keeps flowing.
It does. This ongoing check is often referred to as continuous evaluation. If its effectiveness starts to decline, maybe like that cake recipe tasting subtly different due to seasonal ingredient changes, or maybe customer preferences shifting unexpectedly, it signals that the model might be experiencing that data drift or concept drift we mentioned. This is a strong indicator that the model needs retraining, maybe recalibration, or sometimes even a complete redesign to remain relevant and accurate.
So you have to keep checking.
You have to. This ongoing check is vital because real-world data is inherently dynamic. Trends shift, user behaviors evolve, underlying patterns can change over time. A model trained on yesterday's data might become stale surprisingly quickly in a rapidly changing environment.
So it's like a perpetual feedback loop, always ensuring the AI is kind of up to date and adapting. That makes so much sense.
It is.
Now let's really dive into the how. How is model evaluation actually done? What are the key ingredients or like the practical steps involved?
Right. So there are two main ingredients here, and they really work together. First, we have model evaluation techniques.
Okay.
These are akin to the overall baking process itself.
Yeah.
The strategy.
The structural approach, kind of?
Precisely. These are the systematic strategies for structuring how you assess a model's performance, and they primarily involve how you prepare and segment your data.
Data splitting, right?
Exactly. Typically involves data splitting. You take your entire data set and you carefully divide it into different subsets. You'll have your training data, which is usually the large portion of the data set that the model actually learns from, analogous to our chef practicing that recipe countless times.
Got it.
And then you have your testing data, which is a separate, entirely unseen portion of the data that the model is evaluated on.
Unseen is key.
Absolutely key. This mimics that unseen Real-world data, like actual customers tasting the cake for the very first time, without any prior exposure to it. The model should never have seen the test data during its training phase.
And what are some of the common ways, the common techniques for doing this essential beta splitting?
Well, the simplest and maybe most straightforward is holdout validation.
Okay.
This just involves a single, fixed split of your data. For example, you might take 80% of your data set for training and hold out the remaining 20% for testing.
Simple enough.
It's quick and easy to implement. However, a potential drawback is that the evaluation result can sometimes be a bit sensitive to which specific data points happen to randomly end up in the training versus the testing sets.
Oh,
This
okay.
could be particularly problematic with smaller data sets, where maybe a bad random split might lead to a skewed or unrepresentative performance estimate. You might get unlucky with your 20%.
So if that randomly selected 20% for testing isn't truly representative of the whole picture, you could get a misleading result, almost like having a biased taste panel judge your cake.
You've got it exactly. So to mitigate that risk and get a more robust, more reliable evaluation, we often use K-fold cross-validation.
K-fold. Okay, sounds more involved.
It is a bit more involved, but much more reliable. Here, you divide your entire data set into K equally sized sections, or folds. Let's say K is 5, so you have 5 folds.
Oh, okay.
The model then trains on K1 of these sections, so 4 folds, and tests on the remaining 1 fold.
Right.
Then, this whole process is repeated K times, 5 times in our example, with a different fold held out for testing in each iteration.
Ah, so each piece gets to be the test set once.
Exactly. Finally, you average the results from all K iterations. This ensures that every single data point gets a chance to be in the test set at some point, providing a much more comprehensive and statistically reliable estimate of the model's true performance.
That sounds like a much more thorough taste test, where different groups of tasters get different slices of the cake, but everyone eventually gets to try a piece and you get an overall consensus.
A perfect way to put it. That's
Uh-huh.
exactly the idea. And then there's an even more exhaustive approach, though less common in practice, called leave one out cross-validation.
Leave one out.
Yeah. This is an extreme version of K-fold, where K is actually equal to the total number of data points you have.
Whoa.
So you train on almost all of your data, leaving just one single data point out for testing. And you repeat this process for every single data point in your data set.
That sounds incredibly computationally expensive.
It is. It's incredibly computationally intensive and usually reserved for very small data sets or specific research contexts where that absolute maximum rigor is paramount, not something you typically do for large industrial models.
Okay. So these techniques hold out, K-fold, leave one out. They provide the structure for testing the model, like deciding how to mix ingredients, bake time, temperature.
Right, the framework.
What about the second ingredient, the actual judging of the cake's quality? What metrics do we use to score its performance?
Right, that brings us to the evaluation metrics. These are the specific numerical scores that quantify the model's performance on its given task. They provide the objective, measurable output of your evaluation process, the actual grades, if you will.
Are these metrics different for different types of AI tasks? Like, is judging a model that categorizes things different from one that predicts, say, a stock price?
Absolutely. The choice of metrics is entirely dependent on the problem type. They're not one size fits all.
Okay.
So for a classification task, where the model is deciding if something belongs to a specific category, like is this email spam or not spam? Is this image a dog or a cat? We have several key metrics.
Right.
Accuracy is the simplest one. It's just the overall proportion of correct predictions. For example, if 90% of emails are correctly identified as either spam or not spam, that's 90% accuracy.
Sounds good. But you mentioned earlier it can be misleading.
It can be surprisingly misleading, yes, especially in situations where one category is far, far more common than another. We call this class imbalance.
Okay.
Consider a medical diagnosis model for very rare disease. Let's say only 1% of the population actually has the disease.
Right. Very rare.
A model that always predicts no disease, just guesses no, every time would achieve 99% accuracy.
Wow. Yeah. That sounds fantastic on paper.
It does. But critically, it would completely miss every single person who actually has the disease.
Which is a terrible outcome. Catastrophic, even.
Exactly. A catastrophic outcome in a real-world scenario. That's precisely why we need more nuanced metrics like precision and recall. Accuracy alone isn't enough there.
Okay. So tell us about precision first. What does that measure?
Precision asks a specific question. Out of all the predictions the model made for a certain category, like spam, how many were actually correct.
Hmm.
So for our spam example, if the model predicted 100 emails were spam, and maybe 80 of those truly were spam, the other 20 were legitimate emails that got wrong, then its precision for the spam category is 80%.
Okay. When is precision particularly important?
Precision is crucial when false positives are costly, meaning when mistakenly identifying something as positive, like spam or fraud, has a high penalty.
Right.
Imagine a fraud detection system. You don't want to falsely flag too many legitimate transactions as fraudulent, right? That seriously inconveniences your customers and might even drive them away. You'd prioritize high precision to avoid crying wolf too often.
So precision is about minimizing those false alarms. Makes sense. And recall, what does that focus on?
Recall asks the opposite question. Out of all the actual items that belong to a certain category, like all the real spam emails, how many did the model correctly find or catch?
Okay.
Sticking with spam, if there were 100 actual spam emails that came in and your model successfully caught 95 of them, maybe 5 slipped through to the inbox, its recall for spam is 95%.
And when is recall the most vital metric?
Recall is vital when false negatives are costly, meaning when missing something important has a high penalty.
Like the medical diagnosis example.
Exactly. In that medical diagnosis example for the rare disease, you absolutely want a high recall. You want to ensure you miss as few actual disease cases as possible, even if it means accepting a few more false positives that can then be retested or investigated further.
Right, because missing a critical diagnosis is far, far worse than maybe doing an unnecessary follow-up test.
Precisely. The cost of a false negative there is potentially life-threatening, while the cost of a false positive might just be another test. So you prioritize recall.
And I think you mentioned these too. Precision and recall can sometimes be in tension.
They often are, yes.
Yeah.
There's usually a trade-off. Improving one can sometimes hurt the other. For example, if you make your spam filter super aggressive to catch absolutely everything, high recall, you might end up flagging more legitimate emails as spam, lower precision.
Ah, okay.
So because of this trade-off, and especially when you have those imbalanced data sets we talked about, we often combine them into a single metric called the F1 score.
F1 score.
Yeah, it's the harmonic mean of precision and recall. It provides a balanced view of both, giving you a single number that reflects a model's ability to be both precise and capture most of the relevant cases. It's very widely used.
Got it. What about when the model is predicting a number, not just assigning a category, like predicting house prices or maybe the temperature tomorrow?
Right. For regression tasks, where the model's output is a continuous numerical value, we use different metrics entirely.
Okay.
A very common one is mean squared error, MSE.
MSE.
This metric calculates the difference between the model's predicted value and the actual observed value for each data point, squares that difference to penalize larger errors more and ignore the sign, and then averages these squared differences across all data points.
Okay, so lower is better.
Yes, a lower MSE indicates that the predictions are, on average, closer to the true values, meaning the model is generally more accurate. Another widely used metric for regression is R-squared, R-rote, which is also known as the coefficient of determination.
R squared, what does that tell you?
R-squared indicates how well the model's predictions fit the observed data. It represents the proportion of the variance in the dependent variable, the thing you're trying to predict, that is predictable from the independent variables, the inputs to the model.
So higher is better here.
Yes, a value closer to 1 or 100% suggests that a larger proportion of the variance in the target variable can be explained by the model. It essentially tells you how much of the variation in the output is captured by your model. A score of 0 means the model explains none of the variability.
Okay. And I imagine for these complex language models that, generate text like summaries or translations, there are completely different metrics, yet it seems like a whole other ballgame.
You're absolutely right, it is. For natural language processing, NLP tasks, especially those involving language generation like machine translation or text summarization, we use highly specialized metrics.
Like what?
Two prominent ones you'll often hear about are BLEU, which stands for Bilingual Evaluation Understudy, and ROUGE, Recall-Oriented Understudy for Gisting Evaluation.
BLEU and ROUGE. Okay.
These metrics evaluate the quality of machine-generated text by comparing it computationally to one or more human-generated reference texts, like professional translations or summaries.
How do they do that comparison?
Well, they essentially look at the overlap of n-grams, which are sequences of n-words between the generated text and the reference text. BLEU focuses more on precision. Did the n-grams in the machine output appear in the reference? While ROUGE focuses more on recall. Did the n-grams in the reference appear in the machine output?
So they're trying to quantify how similar or good the generated output is.
Exactly. In terms of fluency, adequacy, and capturing the key content, it's like judging your cake's appearance and structure. Does it look appealing? And is it consistent with the ideal master pastry chef's creation? BLEU and Rouge try to do that for text.
So these metrics are like judging your cake. Are the flavors coming through accurately? Accuracy, precision recall. Does it have a pleasant, consistent texture? MSE. Does it look appealing and structured correctly? Literature.
That's a great way to summarize it.
They provide the precise scores within that overall evaluation structure you set up with the techniques.
Precisely.
That's a really helpful way to think about it. Now, given all these options, different techniques, tons of different metrics, how do you actually decide which ones to use for a particular AI project? It sounds like there are a lot of choices to make.
Yeah, there are. And the choice is anything but arbitrary. It's really a strategic decision guided by several critical factors.
Okay, what's first?
First, and most obviously, is the model type. Is it a classification problem, a regression task, an NLP generation task, something else? Each inherently demands different kinds of evaluation metrics and sometimes different techniques.
Makes sense. You wouldn't judge translation with MSE.
Exactly. Second, and perhaps most important, is the project goal. What exactly is most critical for your specific application? What does success look like in the real world?
Right.
As we discussed, for that medical diagnostic model, recall might be absolutely paramount to ensure no actual disease cases are missed, even if it means tolerating a few more false positives. But for a spam filter, maybe precision is more important to avoid sending legitimate emails to the junk folder and frustrating your users. You need to define what matters most first.
So it really depends heavily on the real-world costs of different types of errors.
Exactly. The cost of errors is a massive factor. How severe is a wrong prediction in this context? A false negative in an autonomous vehicle's object detection system is, well, catastrophically worse than a bad movie recommendation.
Right. Very different stakes.
Very different stakes. This directly influences which metrics you prioritize and how rigorously you need to evaluate potential failures. Also, dataset size matters.
How so?
Smaller datasets might necessitate more sophisticated cross-validation techniques like K-fold to ensure you get statistically reliable results, whereas very large datasets might make simpler holdout validation more practical just due to the sheer computational cost.
Right.
Some techniques, like leave one out, are simply too resource-intensive and time-consuming for massive datasets. You always have to balance that desire for thoroughness with practical constraints like time and budget.
And then there's that nuanced concept of overfitting and underfitting that we often hear about in ML circles. How does Evaluation Guide dealing with those?
That brings us to the crucial bias-variance trade-off. Evaluation is key here. This is all about finding that sweet spot where the model generalizes well to new data.
Okay.
We need to ensure the model isn't overfitting, which, again, is like that student who memorizes every single practice test answer and performs brilliantly on those specific questions, but then utterly fails the real exam because they can't generalize.
Right. Learned the noise, not the signal.
Exactly. Or conversely, we need to avoid underfitting, which means the model's too simple, it hasn't learned enough from the data, and performs poorly even on the training data itself. Like a student who barely studies and understands nothing. Robust evaluation techniques and metrics help us diagnose whether we're overfitting or underfitting, and guide us in adjusting the model complexity or training process to manage this trade-off effectively. We want a model that's just right for its task. And finally, related to what we discussed with accuracy, data balance is critical.
The imbalance classes issue again?
Yes. If one category in your data is very rare, a minority class, standard accuracy alone can be incredibly misleading, as we saw vividly with the rare disease example. In such cases, metrics like precision, recall, F1 score, or others like the area under the ROC curve, AUC, become far more informative and essential. And really, as a general best practice, you should always use multiple metrics in combination.
Don't rely on just one number.
Never. Get a truly well-rounded, comprehensive view of your model's performance from different perspectives. Relying on just one score can easily hide critical issues or weaknesses that could undermine your AI system once it's deployed in production. You need the full dashboard. 3. The stakeholders. Who cares about model evaluation results?
Wow, okay. This sounds like an incredibly intricate and just fundamentally vital process. So it's clear this isn't just some technical exercise for data scientists toiling away in a lab somewhere, is it?
Not at all.
It really sounds like the results of model evaluation ripple out across a much wider audience. Who are these people who actually care deeply about how well an AI performs? Who needs to see these results?
You're absolutely right. The audience for model evaluation results is surprisingly broad and diverse. It's not just the techies. First and foremost, of course, are the data scientists and ML engineers themselves.
The builders.
Exactly. They're the architects, the builders, the fine-tuners of these models.
Yeah.
They use the evaluation results as their primary feedback loop.
Okay.
They're constantly refining, enhancing, and ultimately choosing the absolute best models to move forward with based on these metrics. This is their direct insight into what technical adjustments are needed to improve performance, debug issues, or optimize for specific objectives.
It's like the master chef getting those specific, detailed taste notes from food critics and then knowing exactly how to tweak their recipe for perfection next time.
Precisely that. Then you have the business leaders. They aren't typically diving into the Python code or, parsing F1 scores themselves,
Probably not.
but they are intensely focused on the real-world impact. They analyze evaluation results, often summarized or visualized, to understand the direct effect on things like revenue, operational costs, customer satisfaction, market share.
The bottom line.
The bottom line, they use this data to make strategic decisions about model usage. Should we scale this model globally? Does it need a major update? Should we maybe pivot our overall strategy based on how this AI is actually performing? Their key questions are always, does this AI improve our business? Does it make our customers demonstrably happier or more efficient?
And what about the people who actually have to integrate these models into the larger company systems, the software folks?
Right. Those are the software developers and engineers. They're responsible for taking a trained model, which might work great in a data scientist's notebook, and seamlessly integrating it into existing applications, websites, or complex enterprise systems.
That sounds hard.
It can be very challenging. They need to ensure models don't just perform brilliantly in isolation, but that they integrate smoothly, run reliably, don't introduce unacceptable latency, and don't cause system crashes or bottlenecks when they're live and handling real traffic. Evaluation results, especially those related to performance under load or resource consumption, help them understand the model's operational characteristics and anticipate potential integration challenges. A fantastic model that can't actually be deployed reliably is, for all practical purposes, useless.
True. And then ultimately, there's us, the people actually using the AI every day.
Absolutely, the end users. Whether you're interacting with a customer service chatbot, getting a personalized product recommendation on an e-commerce site, using AI-powered features in your smartphone camera, or relying on AI in your daily work tools, you implicitly care about the accuracy and trustworthiness of the AI you interact with. We all want our AI experiences to be reliable, helpful, and efficient.
Right.
Not frustrating, inaccurate, or prone to weird errors.
Definitely.
Our trust in these systems fundamentally hinges on their consistent evaluated performance. We might not see the metrics, but we feel the results.
And in many industries, especially the highly regulated ones like finance or healthcare, there are external bodies involved too, aren't there, watching over things?
Indeed. Regulatory bodies are becoming increasingly important stakeholders in the world of AI evaluation.
Okay.
In sensitive domains like finance, think loan applications, credit scoring, healthcare, diagnostics, treatment recommendations, or employment hiring algorithms, they need tangible proof that models meet specific standards for performance, consistency, and critically non-discriminatory outcomes across different groups.
They need proof of fairness.
Exactly. They demand transparency and accountability. Robust, well-documented model evaluation provides the essential evidence they need to ensure compliance with regulations and to uphold public trust. A model with unquantified, significant disparities in its predictions across different user groups could face serious regulatory scrutiny, fines, or even be pulled from use.
And what about the broader academic and research community? How do they use evaluation results?
Researchers in the broader field of machine learning constantly use published evaluation results to advance the collective understanding of AI capabilities.
Building on each other's work.
Precisely. When models are rigorously evaluated using standard benchmarks and the results are shared openly, it pushes the boundaries of what AI can do. It helps identify new areas for exploration, validates new techniques, and allows the entire community to build upon existing knowledge, accelerating innovation across the board. It's how the field progresses.
So this brings it right back to you, our listener. Why should someone who might not be, building AI models day to day care so much about how they're evaluated? What's the key takeaway here for a broader audience?
That's a great question. Whether you're building the next great AI product, or leading a team that leverages AI, maybe investing in AI companies, or simply curious about the intelligent technologies shaping our world, understanding model evaluation is absolutely key.
Why is it key?
Because it means you can better trust the systems around you. You can ask more informed questions about them. You can make more intelligent decisions based on their outputs. If you're a business leader, it equips you to critically assess the proposals and results coming from your data science team. You can ask, how was this evaluated? What were the key metrics? Did you check for bias?
Right.
If you're an end user, it empowers you to critically evaluate the AI tools you encounter daily. Why did it give me that recommendation? Is this chatbot actually reliable? It transforms AI from this mysterious black box into something you can actually understand, scrutinize, and engage with more intelligently. Ultimately, it empowers you to demand better, more reliable, and fairer AI systems from the companies that build them. 4. Model evaluation within the bigger picture.
MLOps.
MLOps in the AI factory.
Okay, this all sounds like a tremendous amount of moving parts to manage effectively, especially if you're dealing with, multiple AI models, constantly training them, deploying them, and then continuously evaluating them like you described. How does model evaluation fit into the larger ecosystem of actually building and deploying AI in a structured, repeatable way?
That's precisely where MLOps, or machine learning operations, enters the picture. It's the framework that tans that complexity.
Okay, exactly.
Think of MLOps as the comprehensive, overarching framework that governs your entire AI factory.
An AI factory, I like that.
Yeah, imagine you're running a high-tech factory that produces specialized, intelligent tools. Those are your AI models. MLOps is the complete system and set of best practices that ensures this factory runs smoothly and efficiently. It covers everything from the initial design of these AI tools through their precise manufacturing, training, and validation to getting them into customers' hands, deployment, and critically, ensuring they perform well and remain effective over their entire life cycle, monitoring and evaluation.
So it's like DevOps, but for machine learning.
Exactly. It's essentially a specialized form of DevOps, specifically tailored for the unique challenges of machine learning.
And you said it bridges the gap between the lab and the real world.
Yes, crucially. MLOps bridges that often challenging divide between the experimental phase of developing a model, the initial design, coding, creation of your specialized AI tool, often done by data scientists, and its operationalization, which is the whole process of integrating that tool seamlessly into the real world so it can actually perform its function reliably and at scale, whether that's making real-time predictions, automating decisions, or taking specific actions. Without robust MLOps practices, promising AI models often just languish as isolated proofs of concept in a Jupyter notebook somewhere. They never truly make it to scaled, impactful, real-world deployment. MLOps is the bridge to production value.
What are the core pillars then? What holds MLOps up and enables this smooth, reliable transition?
MLOps is generally seen as being built on 3 essential pillars. First, collaboration.
Okay.
It brings together traditionally disparate teams. You've got data scientists, who are the innovative tool designers, software engineers, who are the factory builders and system integrators, IT operations folks, and business stakeholders, who are ultimately the customers or beneficiaries of these tools, all working together in a seamless, unified manner.
Breaking down silos.
Exactly. Breaking down those silos, ensuring everyone is aligned on the model's purpose, its performance metrics, its deployment goals, fostering a shared understanding and language across the entire AI lifecycle.
Makes sense. What's pillar 2?
Second, iteration. MLOps establishes a continuous, often rapid cycle of refining and improving models.
The feedback loop again.
Yes. This involves constantly gathering feedback from production, rigorously evaluating models against new data, and then making necessary updates or triggering retraining automatically. Think of it as continuously gathering feedback on your manufactured tools from the field and then rapidly producing new, improved versions V2, V3, and so on. It's about building a culture of ongoing learning, adaptation, and continuous improvement within your AI factory, not just shipping version 1 and hoping for the best.
And the third pillar, what holds it all together?
Systemization. This provides a structured, often highly automated framework for managing every single aspect of the AI lifecycle.
Like what aspects?
This includes critical components like data versioning, tracking your data, model versioning, tracking your models, automated testing, continuous integration, and continuous delivery, CI/CD pipelines, infrastructure management, and, crucially for our discussion, automated model evaluation and monitoring. Systemization ensures that models remain reliable, their performance can be consistently tracked and monitored, and their entire development and deployment process can be reproduced efficiently and consistently over time. You can rebuild or redeploy any version reliably.
And the goal of all this MLOps machinery.
The ultimate goal of this entire MLOps framework is to deliver ML models that are not only accurate and robust in a lab setting, but also consistently drive measurable business value when deployed in real-world scenarios. It's about productionizing AI effectively.
So MLOps is essentially the blueprint for a highly efficient and successful AI factory. Are there different levels of sophistication for this? Like how mature or automated can this factory be?
Yes, absolutely. We often talk about MLOps maturity levels as a kind of roadmap, outlining how sophisticated and automated your AI factory currently is.
Okay, where does it start?
At level 0, you basically have manual processes. Everything is manual. This is akin to that skilled craftsman making each tool completely by hand.
Right.
Processes are ad hoc, may be inconsistent between projects, highly prone to human error, and incredibly difficult to scale or reproduce reliably. Model evaluation at this level is often inconsistent, frequently performed manually by the data scientist, and relies heavily on individual expertise rather than standardized, repeatable procedures. It's perfectly fine for initial prototypes or small exploratory projects, but it's utterly unsustainable for building and managing production-grade AI systems at scale.
Okay, so level 0 is the starting point. Very manual. What's level 1?
That's level 1, automated ML pipeline. Here, you begin to automate significant parts of the process. It's like having a few specialized machines in your workshop now, not just hand tools. Things like data ingestion and processing, automated model training scripts, and perhaps basic model deployment might be automated, maybe triggered manually. You're moving faster, and there's more consistency within those automated steps. But comprehensive model evaluation might still be largely manual or ad hoc, and the handoffs between stages, like training to deployment, might still require manual intervention. You've got some powerful pieces of the assembly line, but not yet a fully integrated end-to-end system.
And what's considered the ideal state?
The gold standard.
That's level 2. CI/CD, continuous integration, continuous delivery, pipeline integration, often referred to simply as mature MLOps. This is really the goal state for most organizations serious about AI. It's akin to having a fully automated assembly line with continuous integration and continuous delivery woven into every single step.
Wow, so what does that look like?
At this level, the training, validation, testing, and deployment phases are seamlessly linked together, fully automated and orchestrated, often by a dedicated MLOps platform.
Okay.
You have a robust, closed-loop feedback system where continuous evaluation results from production models are automatically fed back into the development process. This can automatically trigger alerts, or even automated retraining or updates when performance degrades, leading to that ongoing rapid improvement cycle.
And it scales.
Crucially, this level offers true scalability. You can easily handle dozens or even hundreds of models, manage frequent updates, and process massive data sets efficiently without manually rebuilding pipelines or processes every single time. It's built for scale and reliability.
And this is where cutting-edge platforms like, say, Google Cloud's Vertex AI come into play, helping organizations actually achieve that mature level 2 MLOps.
Precisely. Vertex AI is truly designed to be like a unified control center for your entire AI factory. It aims to bring together all of Google Cloud's powerful AI and machine learning services, from data preparation and feature engineering to model training, evaluation, deployment, and monitoring, all into one integrated, intuitive platform.
Making it simpler.
Exactly. It significantly simplifies the entire complex ML development lifecycle, helping organizations build, deploy, and scale models with unprecedented efficiency and reliability. Its core design principle is really to help you achieve and operate effectively at that level 2 MLOps maturity we just described.
So how crucial is model evaluation within this Vertex AI ecosystem? Is it just, another feature bolted on? Or is it deeply embedded in the process?
Oh, it's absolutely central and deeply embedded. It's not an afterthought. It's vital that model evaluation isn't just a separate step you do at the end, but is intentionally built into and automated at every single stage of the MLOps lifecycle that Vertex AI supports, from the moment you start building and training your model, right through its deployment and ongoing monitoring.
Why is that embedded approach so important?
This embedded continuous evaluation capability is paramount for proactive risk mitigation. By consistently evaluating models at multiple checkpoints, teams can catch issues early before they become major problems in production.
Like what kind of issues?
This includes potential declines in model performance over time, outright malfunctions where the model just isn't working as expected, or detecting if the model is producing predictions that are consistently different or biased for certain segments of your data. It also helps catch other unforeseen issues that could negatively impact performance or user experience, ensuring the AI is not just effective initially, but also reliable and consistent over its entire lifespan, right from the very beginning of the development cycle. It's baked in. The challenges in model evaluation. Why? It's tricky to grade your AI student.
Okay, so we've covered the what, why, when, and how it all fits into this bigger MLOps picture, ideally with platforms like Vertex AI helping out. But grading an AI student, even with great tools, sounds like it can't be all sunshine and roses. There must be pitfalls.
Oh, absolutely.
What are the common real-world challenges that make model evaluation so tricky, even when you're trying your best?
You're absolutely right. It's far from straightforward. Even the most brilliantly designed AI students can encounter unexpected problems, and there are definitely common challenges that make it genuinely hard to always trust their performance fully or know if your evaluation is really telling the whole story.
Okay.
One of the biggest areas of concern revolves around data issues, which, as we've touched on, are the absolute foundation of your model's learning. Flawed data leads to flawed models and potentially flawed evaluation.
Like a student being taught from flawed textbooks, or maybe just not enough diverse textbooks to cover everything.
Exactly, that analogy holds. The first common data issue we really need to watch out for is overfitting.
Right, we mentioned this, the memorization problem.
Exactly. This is precisely like that student who has memorized every single answer for a specific practice test that's your training data, but then utterly fails to answer similar questions when they're phrased even slightly differently on a new test, which represents new, unseen data. The model performs spectacularly well on the data it has already seen during training, but poorly, sometimes disastrously, on anything truly new or slightly different.
So, like a model trained exclusively on pictures of, I don't know, golden retrievers in sunny parks might struggle to identify a golden retriever at night or in the snow, even though it's the same breed. It becomes too specific.
Precisely. It hasn't learned the general concept of golden retriever. It's learned golden retriever in a sunny park. It's learned the irrelevant noise or specific artifacts within the training data rather than the underlying generalizable patterns.
Okay. What's another big data challenge?
Another significant challenge is data shift or concept drift. We touched on this with continuous evaluation.
Right, the world changing.
Exactly. Imagine you've taught your AI student to identify popular fashion trends from 2020 based on images. If you then deploy it in 2025 without updates, its performance will likely plummet because fashion trends have changed. The underlying concept it learned, what's fashionable, has drifted. This is when the characteristics of the real-world data change over time, making your deployed model less accurate if it's not continually monitored and updated or retrained. A classic example is a financial fraud detection model. Fraudsters are constantly changing their tactics, so a model trained on old fraud patterns will quickly become outdated and ineffective. The concept of fraud itself evolves.
So the world evolves, the data changes, and the model doesn't keep up unless you actively manage it.
Exactly. And what if the initial teaching material, the training data, wasn't diverse or comprehensive enough to begin with?
Yeah, what happens then?
That leads to the challenge of lack of representative data. If you only ever teach your student using examples from one specific textbook or one narrow perspective, they simply won't be equipped to handle the diversity of the real world.
Okay.
Similarly, if your training data doesn't adequately cover all the different variations, scenarios, or demographic groups your model will face in the real world, its performance will suffer, often unevenly, when confronted with those unseen situations or populations.
Like the facial recognition example you gave earlier.
That's a classic stark example. A facial recognition model trained predominantly on images of light-skinned individuals might perform significantly less accurately on individuals with darker skin tones. Not because of any malicious intent in the algorithm itself,
Right.
but simply because the training data did not represent everyone equally. This leads to biased performance, where the model works well for some groups but poorly for others, which is a major fairness concern. Evaluating only on average performance might hide this crucial disparity.
That immediately brings up another challenge we touched on earlier, the danger of metric choice. You warned that relying on just one metric, like overall accuracy, can be fundamentally misleading. Can you expand on why that's such a common pitfall?
Yeah, it's a huge pitfall because it feels intuitive, but it's often deceptive. Think again about that student who scores 99% on a test, but the critical 1% they missed comprised the most important safety questions.
Oh.
Accuracy alone might look great, fantastic even, but it can completely mask critical underlying problems. This is especially true when dealing with those imbalanced classes, where one category is extremely rare but highly important.
Right, like rare diseases or manufacturing defects.
Exactly. In a system designed to detect rare but critical manufacturing defects, if only 0.1% of products are actually defective, a naive model that always predicts no defect would achieve 99.9% accuracy.
Looks perfect.
Looks perfect on paper, but it would completely fail to identify any of the products that are defective, which
Right.
could lead to massive recalls, safety hazards, reputational damage, and huge financial losses. So relying solely on accuracy in such scenarios is just asking for trouble. You absolutely need precision and recall, or F1, to get the full, true picture of performance on that critical rare class.
So it's really about asking the right suite of questions, using
Hmm.
multiple metrics, not just relying on a single, potentially misleading headline number about the model's performance.
Absolutely. You need that multidimensional view.
What about understanding how the model came to its conclusions? That can feel like peering into a black box sometimes, right?
That's the significant challenge of interpretability, especially with many of the most powerful modern models, particularly complex deep learning networks. We often call them black box models
Why black box?
because they can be incredibly intelligent, achieving state-of-the-art performance, but they're also utterly mysterious. They give you the right answer, maybe with high accuracy, but you have virtually no clear idea how they arrived at that specific answer. The internal logic is opaque.
And why is that a problem if it's accurate?
It becomes a major problem when you need to explain why a model made a specific decision. This is absolutely critical in sensitive, high-stakes areas like healthcare, where a diagnosis could be life-altering, or
Yeah.
finance, where a loan denial impacts someone's livelihood significantly. An AI that denies someone a loan, but neither the bank nor the applicant can get a coherent, understandable explanation for why that decision was made. Well, that can create significant trust issues, potential fairness concerns, and major compliance challenges with regulations that require explainability.
So there's often a trade-off. More complex, maybe more accurate models are harder to interpret.
Often, yes. There's frequently a trade-off between achieving the absolute highest predictive performance, which might come from a very complex black box model, and maintaining a high degree of interpretability or explainability. Evaluating this trade-off is part of the challenge.
And tied very closely to that, we have the critical issue of ensuring fairness and avoiding bias in the model's predictions.
Absolutely. This is a profound and increasingly important challenge in model evaluation. As we discussed with representative data, if the data used to train the model inherently contains historical societal biases or reflects existing inequalities in the real world, the model will likely learn and potentially even amplify those patterns.
But the AI learns the bias from the data.
It can, yes. This can lead to discriminatory outcomes where the model performs significantly differently or makes systematically different predictions for various user groups or segments of your data based on sensitive attributes like race, gender, age, etc.
Like the hiring AI example.
Exactly. If a hiring AI is trained on historical hiring data where, for entirely non-performance-related societal reasons, certain demographic groups were consistently underrepresented or overlooked, the AI might inadvertently learn to continue that pattern, effectively discriminating against qualified candidates from those groups.
So the evaluation challenge is detecting that.
Yes, the technical challenge is rigorously evaluating for these performance disparities across different subgroups. It's not just about overall accuracy, but ensuring the model behaves consistently, reliably, and fairly for all relevant segments of the population it serves. This requires specific fairness metrics and careful analysis during evaluation.
And even if you manage to get everything right at the beginning, good data, good metrics, fair model, the world keeps changing, so performance can degrade over time, right? That seems inevitable.
It really is. That's the constant reality of performance degradation over time. Even the best, most thoroughly trained and evaluated AI students can effectively forget things or become less effective if the world around them changes significantly after they've been deployed. Models need that continuous monitoring we talked about because their performance can and often does decline as real-world conditions, user behaviors, or underlying data patterns shift away from what they were trained on.
Like the spam filter example.
Perfect example. A spam filter might become progressively less effective over time as spammers constantly invent new, creative ways to phrase their messages or disguise their links to trick it. The definition of spam evolves. This inevitably requires continuous monitoring, evaluation, and periodic retraining with new examples to stay ahead and maintain effectiveness. It's an ongoing arms race, in a way.
An ongoing battle to maintain peak performance. And finally, just getting the smart model to play nicely with the rest of the school system, so to speak, the practical deployment.
Right. That's the often underestimated practical challenge of integration challenges. Getting your brilliantly evaluated model, which works perfectly in a controlled environment, to actually work smoothly and reliably within the larger production system. The existing software applications, databases, legacy systems, and IT infrastructure can be surprisingly tricky.
What makes it tricky?
It often involves navigating complex technical hurdles, like dependency conflicts, different programming languages, overcoming logistical complexities like scaling infrastructure, and ensuring seamless communication and coordination between different teams like data scientists, software engineers, DevOps, and operations teams. Everyone needs to be on the same page.
Right.
A meticulously evaluated model, no matter how accurate or fair it is in theory, is of limited practical value if it can't be seamlessly deployed, maintained efficiently, monitored effectively, and scaled reliably within a live operational environment. The last mile is often the hardest. Mitigating challenges in Vertex AI's role, making your AI student better.
Okay, so we've laid out a pretty daunting list of tough, real-world challenges in evaluating AI models. From subtle data issues like overfitting and concept drift, to the critical need for fairness, consistency across different data segments, explainability, and just plain integration headaches.
It's not trivial.
But the good news is, presumably, there are robust strategies to address these. It's not hopeless. How do we go about making our AI student truly better, more reliable, and more trustworthy in the face of these challenges?
Exactly. The challenges are significant, but so are the mitigation strategies we can employ. It's definitely not hopeless. First, and critically, as we've hinted, we need to move beyond relying on single, simple metrics and demand comprehensive evaluation with multiple metrics.
Don't just look at the final grade, look at the whole report card.
Precisely. Use many different complementary metrics like precision, recall, F1 score, AUC, MSE, maybe fairness metrics to get a full, multifaceted picture of your model's performance from different angles. This holistic view helps uncover subtle problems or trade-offs that a single, isolated metric might easily mask. Like maybe it has great overall accuracy but terrible performance on a specific important minority category. Multiple metrics reveal that.
So it's about building that truly balanced scorecard for your AI.
Exactly. Next, we need to implement meticulous data validation and preparation.
Garbage in, garbage out.
Feel true. This means carefully checking the quality, cleanliness, representativeness, and potential biases of your training and evaluation data before it ever gets near the model. We also need to use smart techniques during data splitting, like stratified sampling, to ensure that your evaluation data sets reliably reflect the real-world data distribution, including across different important subgroups. Clean representative data is foundational.
And what about that pervasive problem of overfitting, where the model just memorizes the training data and can't generalize to new stuff? How do we stop our AI student from just, rote learning?
Right. Preventing overfitting is key to generalization. We employ several powerful techniques during the model training process itself to combat this. Regularization is a major one.
Regularization.
Yeah, it's like telling your student to focus on the main ideas and general principles, not just getting bogged down in tiny, irrelevant details in the training examples. Technically, methods like L1 or L2 regularization add a penalty term to the model's objective function during training. This penalty discourages overly complex models with large parameter values, effectively promoting simpler, smoother models that tend to generalize better.
Okay, keeps it simpler. What else?
Then there's dropout. This is a technique mainly used in neural networks. During training, you randomly drop out or deactivate a certain percentage of the model's neurons or connections in each training iteration.
Why would you do that?
It forces the network to learn more robust features and prevent it from becoming overly reliant on any single neuron or pathway. It's like making your student learn the same subject multiple times with slightly different parts of their brain, temporarily unavailable. It makes them more resilient and less likely to rely on just one specific way of understanding, improving generalization.
Interesting. And you mentioned early stopping, too.
Yes, early stopping is a more straightforward but often very effective technique. It's like stopping your students studying right when they're at their peak performance on practice questions that weren't part of the main study material before they start getting tired and making silly mistakes or just over-memorizing the noise.
How does it work?
You monitor the model's performance on a separate validation data set, not the final test set, during training. When the performance on this validation set stops improving or maybe even starts to get worse, indicating overfitting might be starting, you simply stop the training process, even if performance on the training data itself is still going up. You save the model from that peak validation performance point.
Clever. All about promoting smarter learning, not just brute force memorization.
Exactly. And because the real world is constantly changing, as we've established, model monitoring is absolutely crucial after deployment. You can't just deploy and walk away.
Right.
You must continuously watch your model's performance in production, ideally using automated tools that track key metrics and can automatically detect significant performance degradation or shifts in data patterns, drift, that indicate the model might be becoming stale or inaccurate.
So you catch problems early.
Yes, this proactive approach allows you to intervene, maybe trigger retraining, or investigate the data shift before performance issues become critical and start negatively impacting users or business outcomes.
And the really critical challenge of ensuring fairness and consistency across different segments of your data. How do you specifically mitigate that during evaluation?
For ensuring fairness and consistent performance across different data segments or subgroups, we need to rely on specific metrics and tools designed for fairness or performance disparity analysis.
Going beyond overall averages.
Absolutely. This involves using specialized evaluation metrics that explicitly quantify if your model is performing differently for various groups within your data. For example, calculating accuracy or error rates separately for different age groups, genders, races, or geographical regions. There are tools and libraries specifically designed to help with this segmentation and analysis. It allows us to systematically identify and potentially address any significant performance gaps or biases, ensuring the model is robust and reliable across the entire spectrum of its intended use. It moves the evaluation beyond just overall averages to ensure equity.
And finally, that challenge of understanding the why behind those inscrutable black box decisions. How do we shed light there?
That's where explainability tools come into play. They're becoming increasingly important. Tools like LIME, Local Interpretable Model Agnostic Explanations, and SAP, Shackley Additive Explanations, are invaluable here.
Lime and SAP, how do they work?
Well, they don't exactly open up the complex black box model itself. Instead, they work by providing explanations for individual predictions. For example, LIME works by building a simpler, interpretable model, like a linear model, in the local vicinity of a specific prediction to approximate the black box's behavior just for that instance. SHAP uses concepts from game theory to attribute the prediction outcome to the contribution of each input feature, basically saying how much each input pushed the prediction one way or the other.
So they give you clues about specific decisions.
Exactly. They make the model's thinking for a particular case more transparent. This is vital for building user trust, for debugging unexpected or incorrect model behaviors, and increasingly for meeting regulatory requirements that demand explainable AI in certain sensitive applications.
Okay, so those are the general strategies for mitigation. Now let's tie this back explicitly to a platform like Vertex AI. How does this super smart teaching assistant you mentioned earlier really elevate this whole evaluation process and actively push an organization towards that mature, reliable level 2 MLOps?
Right. Vertex AI is designed precisely to provide the powerful integrated tools needed to implement these mitigation strategies effectively and, crucially, at scale. It's not just about manual checks anymore. For instance, it enables iterative evaluation at scale.
What does that mean in practice?
It means you can easily configure and run evaluation jobs repeatedly on new datasets, maybe daily or weekly, even if those datasets are massive. This allows you to continuously check model performance as new data streams in or as you retrain models. You're not stuck with a single static assessment done months ago. You have a dynamic, ongoing performance snapshot integrated into your workflow.
And for comparing multiple model candidates or maybe different versions of the same model after retraining?
Vertex AI offers advanced visualization and comparison tools specifically for this. It provides intuitive dashboards and clear visual comparisons of different models or different trained versions of the same model across a whole range of metrics simultaneously.
Making it easy to see the winner.
Yes, it makes it incredibly easy to quickly grasp performance differences, understand trade-offs, like maybe one model has better precision but worse recall, and confidently choose the best model or version for production based on comprehensive side-by-side data. Imagine seeing clear interactive graphs showing which version of your AI tool is most durable, accurate, or consistent across all the performance dimensions you care about.
And specifically addressing that critical challenge of consistency across different data segments, which we discuss is often hidden by overall averages. Does Vertex AI help there?
Yes, this is a key strength. Vertex AI allows you to easily assess performance across slices of your data.
Slices.
Yeah, slices are just defined segments of your data based on specific feature values. So you can configure it to automatically calculate and display performance metrics, not just overall, but broken down by different segments. For instance, how well does your image classification model perform on images taken during the day versus at night? Or how well does your sentiment analysis model work for text from different languages or regions?
Oh, okay.
This capability is absolutely critical for identifying and addressing those potential performance gaps or biases that might otherwise go completely unnoticed when you're only looking at the aggregate top-line metrics. It helps ensure your model is reliable and consistent for all relevant user segments it's supposed to serve.
And how does it ensure that robust, continuous improvement loop that's so essential for level 2 MLOps, the automated response?
It helps establish a truly robust feedback loop. By deeply integrating model evaluation and monitoring directly into your automated training and deployment pipelines, which Vertex AI pipelines facilitate, the platform can automatically detect if a deployed model's performance begins to degrade significantly in production below predefined thresholds. When that happens, the system can be configured to automatically trigger alerts to the right teams, or even automatically kick off a retraining job using new, updated data.
Closing the loop automatically.
Exactly. This ensures your AI tools always stay sharp, relevant, and accurate without requiring constant manual intervention and oversight. It maintains that continuous flow of high-quality, up-to-date AI in production.
So it's not just about running checks periodically, but about automating the intelligent response to those checks failing.
Precisely. It moves from reactive to proactive and automated maintenance. It also provides built-in mechanisms for running fairness checks as part of the evaluation, allowing you to systematically quantify and monitor for those performance disparities across different groups, making fairness assessment a routine part of your development process rather than a special one-off audit.
Okay.
Furthermore, its overall streamlined workflow guides you through the entire evaluation process logically. You train your model, maybe using Vertex AI training, then you run batch predictions on your evaluation data, you prepare the ground truth or answer key, often stored in BigQuery or cloud storage, then you initiate the evaluation job within Vertex AI evaluation.
And it does the comparison.
Yes. Vertex AI compares your model's predictions to the ground truth and automatically calculates a suite of relevant metrics. Finally, you analyze the generated metrics, often visualized in the console, understand where the model excels or fails, and then iterate to improve your model, closing the loop. This structured approach simplifies an inherently complex process, making best practices easier to follow.
And it sounds like it handles a lot of different data types, too, not just numbers and tables.
Yes, Vertex AI is incredibly versatile in this regard. It supports evaluating models for images, classification, object detection, text, classification, sentiment, eventually generation metrics, video intelligence tasks, and of course, traditional tabular data for classification and regression. This makes it a crucial, all-encompassing tool for building reliable, consistent, fair, and responsible AI models across a wide spectrum of common enterprise applications.
So pulling it all together, what does this all mean for the big picture of AI development and deployment for organizations using a platform like this? What's the ultimate benefit?
The overall impact of leveraging a mature platform like Vertex AI for model evaluation within a broader MLO strategy is genuinely transformative for most organizations. You not only significantly increase the quality, reliability, and trustworthiness of your machine learning models, but you also dramatically accelerate your entire journey towards achieving and maintaining a mature, production-ready MLOps environment.
Okay.
This means your AI factory becomes incredibly efficient, highly reliable, and consistently capable of producing high-quality, business-driven AI tools that you can truly trust, scale effectively, monitor continuously, and integrate seamlessly into your core operations. It really moves AI from being an experimental novelty or a fragile prototype into being a dependable, scalable, strategic asset for the business. Outro.
Wow, what a deep dive indeed. We've truly unpacked the crucial and maybe more complex than expected role of model evaluation today.
It's definitely got layers.
Absolutely. From understanding what it actually is, that essential quality control for your AI recipes, and really grasping why it's so pivotal for ensuring true performance, generalization, and making informed business decisions,
Hmm.
to exploring the when and how of its execution with techniques like data splitting, cross-validation, and that whole host of powerful, specific metrics for different tasks.
Yeah, accuracy, precision recall,
Mhm.
F1, MSE, R squared, BLEU, Rouge. Lots to consider.
And we didn't shy away from the complex real-world challenges either, did we?
No, got to face those head on.
We looked at everything from those insidious data issues like overfitting and concept drift to the critical demands of interpretability and ensuring fairness and consistent performance across different data segments, right through to the inevitable performance degradation over time and integration headaches.
They're all part of the landscape when you're building real AI.
But just as importantly, we saw how robust mitigation strategies, things like regularization, dropout, early stopping, continuous monitoring, fairness tools, explainability methods paired with powerful integrated platforms like Vertex AI, provide the essential solutions needed to build truly reliable, consistent, and production-ready AI systems.
That's the key takeaway. The challenges are real, but the tools and techniques to manage them are evolving rapidly too. It really is the sophisticated quality control system that underpins all effective, trustworthy machine learning in practice.
It's truly a foundational piece of the entire AI puzzle, isn't it? Not just an optional add-on.
Absolutely essential.
And for you, our listener, whether you're building the next great AI product or leading a team that leverages AI, or maybe you're just curious about the intelligent technologies shaping our world, understanding model evaluation, at least at a conceptual level, is really key to trusting and making profound sense of the intelligent systems that increasingly surround us in our daily lives. It empowers you to be an informed, critical participant in this ongoing AI revolution, not just a passive consumer.
Well said. And maybe here's a final thought to mull over until our next deep dive. As AI becomes more and more deeply integrated into our daily lives, making decisions that affect everything from our healthcare outcomes and job prospects to our financial opportunities and even the news we see.
Right, the stakes are getting higher.
They are. How much do we, as end users and citizens, need to understand about how its decisions are evaluated? And perhaps even more critically, how transparent do those evaluations, especially regarding fairness and reliability, need to be?
That's a big question. How much insight should we demand?
Exactly. Something to consider as AI continues its remarkable and sometimes slightly scary evolution.